my area of expertise is not exoplanets, so I just want to be careful about that. My training is small inorganic solid things, fancy engineered rocks. However, I did have an undergraduate, Sam, who was doing their honors thesis. And Sam was a chemistry major who graduated 2 years ago. And they are very interested in exoplanets, habitability, things of that sort. So a lot of this work is actually the analysis done by Sam. I would have had them come in to do the talk, but they're not in town anymore. So this is not my work. I do not want to claim it's my work, but it's really neat stuff. And Sam did a great job of putting it together. So exoplanet exploration. Background basics, a little bit to go over. What makes a planet? So nowadays, thanks to the International Astronomical Union, you got 3 things that have to be true. Orbits a star, covers a lot of materials, has sufficient mass to maintain a hydrostatic equilibrium shape, really fancy way of saying it's a ball, and then has cleared the neighborhood around its orbit. This was kind of a add-on to the definition of a planet, because the first 2 make sense, okay, but then they started looking at, there's a lot of round things in our solar system. So if we only kept the first 2 criteria, we don't teach kids 9 planet names, we have to teach them like 5,000. And so I think they wanted to make planets more special. So bye-bye to Pluto, Ceres, things like that, no longer qualify as a planet. Depending upon who you talk to, they're dwarf planets, they're maybe planets, they're icy balls of snow and dust, but no longer officially a planet. So in our solar system, we've got the terrestrial 4, we've got gas giants like Jupiter and Neptune, we've Jupiter and Saturn, and then we've got Neptune and Uranus that make the ice giants. But we don't actually have super Earths in our own solar system. So this 4th criteria, this 4th collection, is a new type of world that we now believe exists, and are actually quite common. They make a pretty large population. So gas giants, these are essentially failed stars. Jupiter is a prime example of one. The gas giants that we have discovered, thanks to Kepler and TESS and ground-based studies and lots of different data collection out there now. Initially, the things that we found were the easiest ones to find, and these were these really large, massive objects, Jupiter-like objects, that were really close to their parent star, and that gravitational tug every few days as it was whipping around would literally make the star wiggle and wobble. And so you were able to measure that spectra shift Doppler-wise. And so those were some of the earliest observations. So early on in the investigations, we thought the universe was full of large, hot Jupiters exclusively, except for the whole, data bias, because that's what the science was really good at finding. It wasn't necessarily really what was actually out there. But that's what our first exoplanets are. Thanks to really good spectroscopy, we're now able to figure out that there are multiple types of these things. In addition to the hot Jupiters, there are several that are further out. And we can even tell that they have different types of clouds due to the spectroscopy. So they're ammonia-based. Jupiter and Saturn are prime examples of those. There are water cloud ones, cloudless. So that's just a hydrogen atmosphere without clouds. A little bit of helium as well. Alkali metal clouds, so that's pretty cool. That to me speaks of a very late forming system after the star death has populated over and over and over. Okay, so those are some of our large gas giants. Neptunian ice giants, so these are going to be similar in size to Neptune, Uranus. Hydrogen, helium as well, but they're going to have more complicated atmospheres, higher percentages typically of the heavier elements, more dynamic atmospheres in that sense. But they're much, much smaller. In both cases, you're talking about a rocky or metal core, whether it's the ice giant or the gas giants. In the case of the gas giants, the larger of the two, there may be enough pressure that the core is actually liquid metallic hydrogen. We have no way yet on Earth of creating such a material, but I'm sure some lab is going to try at some point to do that. Super Earths come in about 3 to 10 times the size of Earth, and we're talking about the mass. Radii up anywhere from size of about 2 times Earth to maybe 3 or 4 times the Earth, because the volume instead of area. All right. These come in a lot of varieties. They are water worlds. So as indicated, for example, by the one on the right, there are snowball planets. They could be rocky, so very similar to what Earth would look like. Because of their larger size than Earth as a comparison, they're going to have more active cores. They're going to have more thermal energy inside. They're going to stay, most likely, more geologically active than a smaller world. We see that in our own solar system. Mercury is basically dead. Mars is close to dead. The moon, not necessarily a planet, but relatively dead. Venus and Earth still have some geological activity. Mars, just a tiny fraction, depending upon how old you consider a volcano to be before it's no longer active. So size does help. The bigger you are, the more that heat stays in there. With that being said, geological activity means recycling of resources. And so you're constantly turning over the surface, which then allows for minerals, nutrients to repopulate the surface. All right. So there are potentially able to support life, depending upon where it is located next to its parent star. And then you got things like Earth or Venus or Mars, terrestrial planets. These can be rock, primarily silicates, water and or carbon rich. Many are most likely going to have atmospheres and or oceans. There are some unusual versions of what they refer to as terrestrial planets. So a silicate planet, Earth, is a silicate crust. That's what most of our rocks are, with an iron core. Carbon or diamond planets, where they are so enriched that they basically are a large carbon sink. You can have planets that appear to have very, very high densities and look like they are almost completely iron and nickel. So that might be an example of the core, for example, of a larger planet that somehow lost all of its upper layers. And then you've got things that are icy planets, which, for lack of any better description, are basically like what Pluto is, or the outer moons. So we're going to call those terrestrial, but they're mostly icy water. It's frozen. So what's common? What do we have out there? 5,000 plus planets found. That number keeps going up. At the end of the talk, I put yesterday's tally as it was, but every few weeks, that number keeps going up as they start confirming. So ballpark 5,000 planets out there. 30% are gas giants. 35 are those Neptune-like ice giants. Another third, roughly speaking, are the super Earths, and only 4% are the terrestrials. Again, this is what they've confirmed and found, not what they actually think is out there as a population. There's a bias. It's easier to see the bigger objects than it is to see the smaller ones. So my guess is, as we get better at the data collection, you're probably going to see that percentage of terrestrial go up as we get better at finding them. But right now, they're the hardest ones to see. So that's kind of where we are currently. In addition, I think this is pretty cool. We have now confirmed at least 28, and again, that number keeps growing, rogue planets, which, if we go back to the definition of a planet, is not really a planet. So rogue planets appear to be objects that formed in some form of solar system, and then due to gravitational imbalances, got shot out and are flying free through the system, through the universe, through the galaxy. Some dark, cold world without a star flying through space. But we've got about 28 of those now. How do we find these planets? So this comes off of the NASA, the JPL site. It's where I got this particular database. And currently, when I looked at that again 2 nights ago, they had a total of 5,496 planets. Astrometry has 2, can't see it up there in the corner. Astrometry is probably the closest thing to what an ancient astronomer would have done. You look up at the night sky and you see where the bright dots are, and you see how the bright dots move with respect to each other. They've actually found 2 extrasolar planets that way. They have to have been really, really close objects to pull that off. Right? It is not likely. Somebody got blind luck, is my guess. And then they confirmed it. So let's start off with the big number, transits. I have a bright, shiny object, the star. That star will dim periodically as an object transits in front of it. So this requires close to, if not dead center on that system in order for a transit to work, right? Radial velocity, our next big contender. Whether or not you actually see it transit, if it's a little bit below it or a little bit above it, as that planet whips around in front or behind, it's like when you grab a small kid and you do the spin around type game. You, even though you're much bigger, don't sit still. You have to lean back a little bit when you're pulling that kid, and that wobble that you would experience is what the star undergoes. Our ability to look at spectra, then take a look at the hydrogen lines and the whatever lines, and they'll shift a little bit to the red, a little bit to the blue, depending upon how quickly they move back and forth and how far they move back and forth. You can pick up data about the size of the planet and its orbital characteristics. So that's radial velocity. Then we get into lots of subvariations. So transit timing variations, eclipse timing variations, pulsar timing variations, pulsation timing variations. That whole grouping is basically looking at all of these naturally occurring features. So a pulsar, depending upon its rate, is a very well-defined fixed timing interval, like really, really, really precisely timed. Again, as that planet whips around it, it can adjust that pulsar's timing, not by a lot, but by a tiny amount. And that's enough to then calculate it. Pulsation timing, so you've got variable stars, Cepheids, for example. Those are also supposed to be fairly well-ordered timing sequences. Again, that whipping around the star can tug and pull on it and shift that timing just a little bit forward or a little bit slower in time, and they can use that. Eclipse timing. If you've got a binary star system, again, those 2 objects have a certain orbital speed that we're expecting, but it shows up a microsecond early, for example, or a microsecond late. Something gravitationally must have tugged one of the 2 partners just a little bit. And that variation is another way of doing it. So these 4 variation types are really looking back through the data very carefully with a lot of data mining in that sense. Orbital brightness modulations, and micro lensing. Okay, so orbital brightness modulations. So in that case, the how do I want to say this? The planet is going to be like Venus. We can see it in phase. Now, this isn't going to work for a Venus-sized planet around a star. It's got to be something like Jupiter-esque or one of the larger objects. But as it orbits around, if it's not transiting it directly, but it's below or above, its phase as it's moving around can change the actual brightness that we observe of the star. Again, way off in the decimal points. So somebody's really being careful about their measurements. But that's the orbital brightness modulation. Disk kinematics is when somebody looked at a protoplanetary disk and looked and saw the actual gaps in the disk and used that to make their calculation. So that's a rather unusual one. What did I get? Microlensing. So microlensing is when you've got some other massive object, star typically, could be a black hole, I suppose, and the faint star or the faint light, not from the star, but from a planet, gets amplified as the light passes around either side of that gravitational object and reforms. And so you can get occasional amplification that way. So that would be microlensing. Imaging is literally directly taking a photograph of that planet. We now have the ability to put in star shades, depending upon the manufacturer's name of the device, but essentially a block that wipes out the star's dominating effect so that the pixels aren't saturated and you're actually able to get visual, like 2 pixels across, star is a black spot, and then there's your planet, and then it moves and it moves. And so that's imaging. If you had asked me that when I was in grad school, I would have laughed that somebody would be able to pull that off. But with the adaptive optics, with the new space options out there, it's truly, truly amazing. Truly, truly, truly amazing. Again, 4100 are some form of transiting exoplanet, where you're literally looking at the star dim just a hair's breadth. The other options are new or extremely difficult.
Paul, before you move on,
yeah.
So with pulsar timing and microlensing, that implies that you have a planet orbiting a pulsar, and with microlensing, you're implying a planet orbiting a black hole.
Possibly.
No way that's supporting life, but that's really cool.
We'll talk about that. Yeah,
Okay.
one of the planets I want to talk about is NASA's looked at that, and they've made some very kind of, well, we'll show you in a little bit.
Okay, yeah.
So radial velocity, I kind of talked about that. But the idea as the planet moves forwards or backwards around that star, the star gets pushed forwards and backwards, and so we get that red shift and that blue shift. That's the Doppler effect. That transit, again, the light curve dims. This is way, way not to scale. All right, that dip is maybe 0.1% or something along those lines. And it depends very much on the size of the planet, whatever. But it's quite effective. Direct imaging, not with that particular telescope, probably not going to pull it off. But you're basically doing star shades or coronagraphy where you're actually blocking out that main central star. That requires that system is relatively close, because you have to be able to get the arc seconds, as it were, of separation between the star and the planet. And the solar systems aren't that big of a thing in space, relatively speaking. So it's got to be a close object, and the star itself has to be relatively weak that you can actually block enough of it to see the things that are orbiting it. So again, still surprises me that we can pull that off, but it can be done. And then that microlensing, like I was talking about. Now, it can be, as Ben pointed out, an actual black hole that would be doing it. But usually it's some object that's past parsecs in front of that does the microlensing. And so that one, to me, is almost a really blind stinking luck effect, more than I'm expecting this to happen kind of thing. But they have confirmed it. Okay, what makes a planet habitable? Okay. Idea, according to NASA, is that it can sustain life for a significant period of time. Now, we're not going to define what life is, because no definition of life actually undergoes full investigation. So, but we're assuming some kind of probably carbon-based life form or some other thing. Our ability to understand that basically says there needs to be water. We need some liquid. Although now there's a debate whether it has to be necessarily water. It could be liquid methane, for example. You just need some kind of liquid solvent. In the habitable zone. So the habitable zone of a star depends on a lot of different factors. And you're basically looking for a place that's warm enough for liquid water, right? But not so hot that it boils it away, right? So you've got this range of intensity coming from the star, okay? Odds are we're not going to find beautiful rolling streams on some exoplanet, but maybe we will. Depending upon the type of star, and we'll take a look at the star classes here in a second, but you could have, so we'll take our lovely solar system, which is the lowest group, large band of habitable zone. Notice that they put Earth in that zone, which makes sense. Venus is just on the inside edge. Mars, according to them, is just inside that edge. There are occasionally times where we think there is liquid water on Mars. It is really short-lived, and it is not something that happens all the time. It's usually some underground brine, very, 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 very salty. A landslide occurs and exposes essentially like a little spring of some underground brine. So there technically is occasionally water on Mars in liquid form. Most of it is in frozen form. Is there a question? No, okay. But depending upon the parent star, you could have habitable zones like the Kepler 452 system, which are very similar in size to ours. Or if you go to the Kepler 186 system, which is essentially a red dwarf, that star is not putting out that much energy. And so you can be really close to the star without getting cooked. You actually have to be close in order to maintain that temperature. And so that's kind of the challenge with what Sam was working on. And again, for many of you folks in the audience, oh, be a fine girl or guy, kiss me, is our star classification chart, right? Our lovely sun is a G. So well down on the size scale. But even with that being said, the number of stars that are in the G spot, as it were, the Earth, Sun, lovely spot, there's only about 3 to 4% of those stars in the whole galaxy. 80% of actual stars in the galaxy are these tiny M red dwarf looking things. They're very, very weak emitters. And so they're going to have very tight habitable zones. If you happen to live next to an O star, you would probably have to be out where Jupiter or Saturn is to not get roasted, right? Earth would be a charcoal briquette next to an O star, right? So just again, how hot is the thing that you're sitting next to determines a lot. So image-wise, cooler stars, sun-like stars, hotter stars. The class of the star changes a lot of that. So when Sam did the work, what they did was they classified the different planets based on super Earth, terrestrials, et cetera, based on the information available. They looked at the mass and radius. They looked at the habitable zones as calculated for different star types. And they looked at a Excel spreadsheet that had, when they did it, 4,521 planets. And they made an Excel spreadsheet with all of these planets, and they categorized. Very quickly, they did some filtering that knocked out huge swath of those. They weren't interested in Jupiter types. They weren't interested in Neptune types. They weren't interested in those because, well, they're gaseous and icy surfaces. You're not really going to be living on them, at least not with life as we know it. You could have moons around them that might work, but they were focusing strictly on planets. So they focused on Earths and super Earths only. With that, and I have to give them credit, they created 24 columns of information. Because depending upon the particular survey or whatever, there are a lot of different data points. Some things we have, some of the planets, we have really good information like average temperatures, atmospheric composition, surface gravity, things like that. A lot of the candidate stars out there, or not stars, candidate planets, we just don't have that data. So there's a lot of holes in that Excel sheet. So what they came up with was a list of some really interesting ones that are not going to be good candidates. Courtesy of NASA having some fun, they created some basically, you know, Star Wars-esque movie posters of the really bad planets out there. So the one I like here is HD 189-733b, so the second planet around HD. This far off blue planet will look blue, but don't be deceived. Weather on this world is deadly. The planet's cobalt blue color is basically hazy, blowtorched atmosphere containing glass shards flying at howling winds and sickening spirals, you know, hundreds of miles an hour of flying glass day in and day out. So not exactly the world that you want to visit. And there are other extreme examples that NASA has, but they had fun with their posters. Another good one, weird orbits that can either put you too close or things like that. So weird orbits could be you're just way too tight, or you could have a really elliptical orbit. So kind of like Game of Thrones, where winter is coming. Yeah, the whole thing freezes over to like Pluto and then comes back to Mercury and then freezes over to Pluto. Not likely to be a habitable world, right? So you do have others that are the right size, the right mass, but they're way too close to the star. So the roasted planet was their photo for that one. And then zombie worlds, which gets back to your pulsar. Yes. All right. So pulsar B1257 plus 12 has apparently a planet around it. And this planet is orbiting essentially a pulsar. Pulsars are emitting about the deadliest amount of radiation in a concentrated form you could ever possibly have. There are other objects that put out more radiation, like quasars, right? Entire centers of galaxies. But you could be light years away from a pulsar, and if you're in its beam, you would have a dead world. So any planet orbiting a pulsar is just getting fried all the time. So zombie worlds. All right. I love how they named the three planets, Draugr, Poltergeist, and Fogator. So if you Google those words, you will find various incarnations of mythic undead. Go NASA. So we eliminated lots and lots and lots of candidates. There were roughly 50 with the correct size, radius, and location, but when Sam looked through the data set, there were other factors that must have popped up that kicked them out. Temperature. So even though they were in the right location, they may have had way too high of a temperature. So maybe that planet had a runaway greenhouse effect or something like that that they were able to determine. Some of them have incorrect compositions. So like the diamond, too much carbon, right? Lots of others, just not enough information to validate one way or the other. But Sam came down with several, what they believed are really good candidates for habitability. So got about 5 of these here that I'm going to spotlight. Kepler 442b, okay? Its radius is about 1 1/3 times the Earth. Its mass, about 2 1/3, all right? That combination gives it a specific or a surface gravity of about 1.5, 1.6. So we would all weigh about 60% heavier. on that world, right? Its equilibrium temperature is 233 Kelvin, which converting it to Fahrenheit is minus 40 Fahrenheit. That's the equilibrium temperature, but that's between the poles versus the equator. So depending upon where you lived on that world, there could be a band very close to the equator that might be over the freezing point, right? So that's one candidate. Kepler, it's not 62, it's 62 something. Has a radius, again, about 1 1/4 of the Earth, mass 3.5, not 35. Its equilibrium temperature even colder. So again, these are the best candidates, and it's that bad. So I just want to get that in perspective. What's interesting about this one, they're actually able to measure the axial tilt of an object nearly 1,000 light years from Earth, which again, the precision required to figure that out is absurd. So very, 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 very cool. Again, I've got Earth's data here in each corner to kind of give you a reference. The average temperature on Earth is 288 Kelvin or 59 degrees Fahrenheit. If any of you ever gone caving, the temperature of a cave is about 58, 59 degrees Fahrenheit, day in, day out, winter or summer. That's basically the surface temperature just below the nasty thing called weather. So it gives you an idea. LHS 1140b, again, 1.6, the radius of the Earth, very big on the high end of the super Earths, about 6.4 times Earth's mass. Its surface gravity, you're going to be coming in about 2 1/4, 2.3 times your weight. So that'll be very, very uncomfortable. What's crazy is they've actually been able to estimate, due to the density and other aspects, that there's probably about 4% liquid water on the surface. Again, I just find the fact they're able to publish this data in a peer-reviewed way, so it's not just somebody winging it, it's been validated. I find that very interesting. So there's an interesting comment. This particular star, LHS 1140, is fairly inactive, which has allowed this to have atmosphere and not be erosive. So I thought that was an interesting comment, depending upon the type of star in its stage of life, right? It may or may not be as active in terms of its solar winds and things like that, or flares. So TOI 700 is really close in size to Earth in terms of radius, 1.1 times the size, mass about 1.5. Its gravity, therefore, is going to be about, again, 1.6, right? It orbits its parent star in 37 days. A year is basically the size of a month, right? Now, they're not sure. It may have a runaway greenhouse effect. They aren't very sure. In addition, the solar wind, the RAM and intensity of interplanetary magnetic field are very similar to what we have here on Earth. Again, I find that very neat that they've actually been able to calculate that. One of the challenges with a planet in this kind of proximity to its star, 30-some days away, it may actually be tidally locked. So although its equilibrium temperature is 268 Kelvin, which is a cold 24 degrees Fahrenheit, it still leaves the poles frozen and a larger temperate zone. It may be gravitationally locked. And so the front side may be boiling and the back side may be frozen. So there's that challenge there, depending upon these small proximity orbits tend to tidally lock. And so that's one of the concerns. TRAPPIST 1e, right? TRAPPIST is this very exciting solar system. It has multiple planets, 7 currently that we have confirmed. 2 to 3 are likely within the habitable zone. 1e looks to be the most promising. 90% of the radius of the Earth, 70% of its mass, Its surface gravity is 75%. So you want a weight loss program, move to TRAPPIST-E, and you've already lost 75, or you're down to 75% of your weight, not your mass. It's a weight loss program, not a mass loss. It orbits the star in 6 days. TRAPPIST is a really tiny, dim red star. It is wee little. And so it doesn't put out a lot of light. So its habitable zone is really, really, really close. So one of the challenges with that system is it probably is tidally locked.
When they discovered these, there was an article, and they started to suspect that these tiny red stars are a lot more unstable than our own sun.
Yeah,
And that may make life kind of difficult to.
exactly. Yep, I just saw that. Thanks to the spectroscopy, they know it's a rocky iron composition. It's got a high chance of oceans due to its density. They've even confirmed a compact atmosphere due to the spectroscopy. That's, again, just amazing. This is only 41 light years from Earth. Not that we've got Star Trek or any of these other fancy technologies to get there, but it's pretty darn close, relatively speaking, to the galaxy. So that's pretty exciting, pretty neat. Some of the interesting things about TRAPPIST-1's system, if you were on TRAPPIST-1E, several of those other planets would be as large in the sky as our moon. In terms of flight times, it took Apollo astronauts roughly 3 days to get to the moon. Mostly because they didn't want to smack into the surface so hard. They could have gotten there faster if they wanted to, but flight times and fuel wise. Flight times and fuel wise across that whole system, a week, at worst case across from opposition type positions. So if there are little green men or whatever species of animal, plant, life that's sentient on there, if they've got rockets and stuff, they might actually literally be a multi-world civilization because they actually have more than one planet that are within that habitable zone and within easy flight times. So that's really cool for sci-fi. I don't know where we're going to end up with that, but it's, you know, a good what if kind of pondering. As of last night, the counter is 5,496. They've got 9,770 candidates that have to be validated and checked. And there are 4,229 planetary systems. Questions, thoughts?
Have they ever used the James Webb to peer in deeper?
That is planned work in the works. Yep, they want to use Webb for that. Yep.
So the 5,000 planets,
Mhm.
what fraction of the star systems in the Milky Way have they investigated? One I'm saying. So what's the, you know, like you got about 2 maybe that you could like maybe put a stake in that you could survive on from what I saw, you know, 2 out of 5,000.
Right. So of the 5,000, 2 out of the 5,000. Again, proximity to Earth is how we're getting the resolution to see a lot of these
Oh,
things.
yeah, sure.
And so we're only seeing the local bubble.
Right.
But
I'm saying, you know, like they, you know, are watching transits in
Mhm.
like a small area or a small zone, and that's a certain volume of the galaxy, do you know, like,
I do not know what the percentage is.
so.
I'd have to make a completely whimsical guess. I have no idea.
Okay,
Um,
so there could still be like, you know.
Yeah.
You know.
Where this fits in something like the Drake equation, where you have like this estimate for life in the world. I don't know what the percentage of actual stars that they've looked at that have candidates.
So I mean, exoplanets are what, 20 or 30% of the stars that are out there if they look at.
The estimate according to I think the estimate for exoplanets is in the 20% range
Okay.
of star systems. Yeah. Again,
Yeah.
the challenge is O and B are probably not so useful. A, maybe. G, we know works.
Mhm.
K and M are really, really, really large in number and quantity, but they're going to have really unusual systems compared to what we're used to. Yeah,
You're still talking about like millions of possibly habitable things out there.
well, there's what, 100 million stars in the galaxy? Am I getting my numbers, my memory, the right number of zeros? Billions.
So
And-
100 billion, 20% is 20
It's-
billion,
yeah.
and then a thousand of 20 billion is 20 million. I don't know, maybe.
You're still talking thousands of
Yeah.
likely,
There's a lot still,
Yeah.
but are they close? I don't know.
roughly 41 light years for the Trappist one,
There you go.
which from the galaxy point of view is really close.
Really close. Yeah.
So all these techniques boil down to one thing, looking for change, tell where the planet is, that basically kind of a true statement or false.
Change.
That way they
Change, yes. Either change in and of itself or change of the change that you expect. Yes.
if there's any other techniques on the future or.
No, I take it back. Direct imaging does not require change. So the 68,
See a change in the brightness?
no, the direct imaging is where they have a block that actually covers the star and they see an object on its orbital path around the star.
Yeah.
So that does not require change, except for the fact that I see two dots. To confirm it, those two dots better move around the thing.
Yeah, so there's some.
So there is still change for the confirmation purposes, but direct imaging, you just need that one shot, but to confirm it, you want to see it multiple times to get the orbital dynamics and
I'm
things.
amazed that they can get into temperature, surface temperature and all that other stuff. That's
A lot of it is,
unbelievable.
some of it is based on spectroscopy, so they actually can see the chemical compositions.
God,
And depending upon what's present, you can get an idea of basically modeling. A lot of this is, we see these data points, we can model it theoretically this way. So this is what we think that surface is.
you think, yeah.
Science has gotten us to lots of cool places. So our thinking in science usually comes out close.
Getting better all the time.
Yeah.
Are there any preferences? Do they see any? Is there a preference for the type of star, you know, like, G stars work like you said? But do they see planets that are evenly distributed across the types, or is it specific to some group or another? Some type or another?
I don't remember. That's a really good question. Don't remember. If there is a preferential type that tends to have more. I don't know.
And then again, a lot of your classic sci-fi, you have 2 or 3 stars, in the atmosphere to add dramatic effect to the.
They do have binary star systems with planets.
So it's not an
So
automatic.
Tatooine with 2 stars in the sky. Now, what you'll have is a sun-like object, and then the second star looks really, really dim.
Yeah.
Because it's really far away. You're not going to see 2 bright stars. Something like that, that's going to be gravitationally unstable and things are going to go flying.
Yeah, I think it's Scorpio has its binary companion is 12,000 astronomical units away, which is about 300 times further away than Pluto.
Yeah.
So that would actually not seem to be gravitational effects aside, which I can't imagine. But just from a heat light standpoint, it would qualify for what you just said, and it would be a fairly dim object.
Yeah. Yeah.
compared
It would be a bright star in your sky, but it wouldn't look like a sun. It would look like just a bright star at that point. Yeah. Then,
Of all the techniques you talked about for finding exoplanets, how do you find the rogue planets?
That,
Because like, they're not emitting anything, so it's all reflected light.
yeah, I didn't go down that path, so I can only
Yeah.
conjecture. It's something passed in front of a star,
Right.
and then they realized it passed in front of this star, and then they like, I don't.
There's just gotta be an amazing amount of luck with that.
Yeah, but they had what was it, 28 of them, I think.
Yeah,
So they got lucky 28 times. Somebody did. Which, if you think about the difficulty of finding them, there's got to be a lot of them out there.
yeah.
There's got to be a
That's what I
lot
thought
of
too.
rogue planets out
Like,
there.
we found 28.
'Cause this is essentially a
Essentially
black
black.
object with black background,
Yeah,
right?
right.
Thermally, they're going to be very cold objects, unless they're a huge Jupiter object with some gravitational thermal energy residue. They're basically going to be almost as cold as the background 3 Kelvin or pretty close to it. So I don't know how you would see those things. But the fact that they found 28 kind of screams at me that there must be rogue planets flying through the universe all over the place.
That's kind of scary.
Yeah.
We've got your comfort though.
Yeah.
So, in a solar system like ours, why do some planets form as gas giants and some as rocky?
Okay.
Did the rocky ones just never get big enough to retain the hydrogen, or?
So proximity to your birthplace. At the center of a protoplanetary disk, as everything is collapsing down and spiraling in, 99.9% of it ends up in the star. The rest of the planetary disk is a fragment of the imagination of that star from its point of view. You have more material close to the star. The further you get away, there's less material. However, the closer you are to the star, the warmer you are. Things like iron and nickel, they don't care. They're going to form a solid and they're going to bind, even at thousands of degrees. Hydrogen, helium, oxygen, carbon, these things can't handle that proximity to the star. They're just too hot. They boil off. And so Mercury has a higher density than, say, Venus. It's made of heavier, more dense, harder to boil things than Venus. Earth is an oddball because of our moon collision. It should be a little bit less than Venus, but we're actually a little bit higher because we swallowed a protoplanetary Mars-sized object and ate its core. So we actually ended up with more metal than we should have. Mars has a little bit less solid materials, and it hasn't quite cooled down enough yet to start growing. Out past the asteroids, where Jupiter is, there was less metals out there, but there is now past the frost line, like at a mountain, right? Nothing, snow. Same idea in the solar system formation. Once you get past the frost line, now things like water, CO2, methane, ammonia, a lot of material is now able to condense onto that ball. And so it still started with a rocky world or a metallic world, but it also was able to gather ices. Those ices formed enough mass to then be gravitationally strong enough to keep the hydrogen and the helium. And then it became a runaway effect. So then if you take a look at the solar system, Jupiter's ginormous, Saturn is a little bit less in mass, and it gets smaller and smaller and smaller as you work your way out, because there's just less stuff. Everything freezes at Pluto. There's just not that much there to freeze. And so that's why our system has that form.
So would most systems be like that then? With rocky planets?
We thought so 30 years ago. Ours is a really oddball one. So that explanation for how our system works looks great on paper for us. But as you start to look out there, you get these things like Jupiter-sized objects in where Mercury is, which shouldn't be. And so there are orbital dynamics. One of the reasons why that may have occurred, if there's enough material in the system, as these protoplanetary objects start to coalesce, they're plowing through dust and debris. adding to their size. Their inside track of their planetary side is going to get hit by more material than their outside track. Because the inside track of their planet is closer to the sun. Not by a lot, but by 1 part in a billion or whatever. But that's enough to start to pool on that side. Between that and rotational energy dynamics, they can drift in. Most of the planets where we have them today isn't where they formed. They probably formed in other orbital spots. And for a while, they drifted in their orbits until that protoplanetary nebulous disk finally blew away. And so there are multiple dynamics that go into why we get these weird planets, from our point of view, really close. In fairness, hot Jupiters are the easiest things to find. So it looks like there's a lot more of them in the universe than anything else, but it's because they're the easiest thing to see. So there's trying to work out that bias and figure out, are they really the 1% or are they really the 99%? So there's some of that bias that we have to figure out. Anybody else? Awesome.
Amazing subject you did.
Thank you.
Yeah.
Again, Sam did a lot of the legwork.
But you added some good touches in there. No.
It's the ponytail that
How
helps.
many times did you present it to the club?
Just the second time, right?
Not the third time? I was thinking this
I
was.
know.
I did living in space with like, no, what did I do?
You rescued us when our waves figure didn't show.
Yeah,
That's right.
like space station life and how you die in space and things like that.
Third time in
No, it's
there.
not, it's the second one.
No, but the second.
I think it's only the second.
Okay.
If there was a third one, I have no idea what the other one was.
Okay, so you're a return.
I'm a repeater,
Yeah, so I guess I
Yeah.
know.
like a pulsar.
All right. You probably already got your coasters, but if you want a medal, we'll
I do have those coasters and I like those coasters. I am very happy with those.
Really?
Yep, they're very cool.
Jim makes them every day.
So, I don't know if we're still in Zoom. I'm assuming we are. Just fine.
Oh, I can.
Yeah, we still have people. Okay. So Julie, Jim, are we doing anything else to close out the night or?
I don't know if anybody else is.
Anybody else wants to have comments or anything or talk to people? I guess you're off the hook now.
Right. Thank you.